Welcome to Let's Do It 5.1. In this LDI, we're going to take a look at the meaning of the mean. Okay, we have two means that we're going to study in this class. One is going to come from a sample, which is going to make it a statistic, and the other will come from a population. Let's talk about the sample mean here for just a second. The sample mean has a calculating formula that's given by the following. This symbol right here that you're looking at right there, that's a summation notation, which means add them all up. So the arithmetic mean turns out to be what we usually colloquially call the average, which means add up all the values of the numbers and then divide by the number of numbers. So there's all of our numbers, that would be the x here, okay? And dividing by the number of numbers, well, remember n, that's the size of our sample, okay? So when you do that, when you add up all your numbers and divide by the number of numbers from a sample, you've created a sample mean. And the sample mean is denoted by this symbol right here, x bar. The way we say that, or the way we would read it, is x bar. That's how you say that, okay? So that's x bar right there. All right, so that's what you have when you have a sample mean. What if you had the entire population? Well, if you had the entire population, notice the only difference between this formula and the previous calculating formula is now we're dividing by capital N. And since we're dividing by capital N, that means we must have taken a census, so we have the population parameter, okay? So remember, a population mean is a parameter, and it's denoted by this lowercase Greek m, which is pronounced as mu. Okay, so the way you would say that in English is mu. Okay, so now that's all well and good, but what was the whole rationale behind that? Well, it turns out that the purpose in life for x bar, it espouses all it really wants to do is do a good job of estimating the value of mu. So remember that a statistics job in life is simply to be a parameter estimator, to do our best job as possible at estimating the parameter. Keep that in mind. That's a simple idea, but it's going to come back over and over again. Okay, so let's go take a look at a quick example here where we calculate the mean of the age data that we collected from the Monday, Wednesday, Friday face-to-face section. Okay, so to do that, I'm going to show you how to do it on your calculator. So you may recall from a previous LDI that we entered into our calculator this list of ages, okay, and there were 40 numbers in here. And so you're not going to want to have to do this by hand. This would just be a royal pain to add up these 40 numbers and divide by 40, okay? I mean, you'd be there forever doing this. So it turns out, lucky for us, this calculator's got a pretty robust stat package built into it. So if you go to Stat, and then from there you go to Calc, and you take a look at that first option, which is one variable statistics. Hit an Enter. I'll paste that back out to the home screen for you. And now you got to tell it what do you want the one variable summary stats of. Well, hit second and then stat to get the names of all the lists that are in your calculator, and I see age resides as option number 7 here, so I'll hit the 7. And notice it's built the command, give me the one variable or summary statistics for the list age. So I hit an Enter, and voila, all the numbers that are fit to print come up, and we see that we get an average age for those folks of 26.5. We also see lots of other numbers here. The sum of the x's, well, that says there's 1,060 years worth of experience in that room. Sum of the x squareds, right now not much need for that, but in later work we might need it. And then those other two numbers there, that's the sample standard deviation and the population standard deviation. We'll talk more about those soon. Now you may ask, where's mu in here? Well, since the calculating formulas for x bar and mu are the same, you've got to do a little bit of interpretation. If you know that this n that you're looking at right here, if that n is in fact a capital N, in other words, that's the size of the population, then you know that this is actually mu. So they're calculated the same, so there's no reason to waste the real estate putting them in there twice. All right, let's go back to our regularly scheduled slideshow here and see if we can go ahead and first of all talk a little bit about the measurement of the mean. First of all, suppose in this particular example you've got a sample of 100 obtained from a population. Can the mean be larger than the maximum value or smaller than the minimum value? Well, after you thought about that for just about 30 seconds, hopefully you realize that no, that can't happen. That the mean as a measurement of center has got to be somewhere between those two numbers. Okay, well, can the mean be the same as the maximum value or the minimum value? Well, at first you may be inclined to say no to that, but let's say you're going to my daughter's 8th grade math class and you ask everybody what their age is, and you get everybody in the class gives you the same response. They're all 13 years of age. So in this case, notice that the mean would be the same as the max, the same as the min, won't it? In fact, all of those numbers will be the same. Can the mean be the exact midpoint of a distribution? And it turns out the answer to that question is yes, if the distribution is symmetric. That's an important idea. So we're going to symmetric. There we go. We're going to definitely come back to that idea. So keep that in mind. Can the mean not be equal to any of the data points collected? Well, yeah, of course. We've all heard the classic example of there being 2.38 children per family, okay? It's not necessary for the mean to be one of the data points. In fact, it's pretty common that the mean is not equal to any of the data points collected. Okay, let's go actually do LDI 5.1. And let's look at this particular example. It says the mean is not always representative. So Kim has the following scores that she's taken on her tests, all right? So she's got some pretty bad scores here, doesn't she? She's got 1, she's got a 7, and then she's got a 25, she's got a 19, and she's got a 26. And miraculously, she had a 98 on one of her tests, okay? So what we want to do is go ahead and calculate Kim's test scores, or mean test score. So we'll do that with the calculator. So I'm going to go back in the calculator, go to Stat, go to Edit, and since this is data I'm not going to use again, it's just going to be for this one LDI, I'm just going to go ahead and put these numbers into L2. Okay, so let me shut down the screen here so I can see what I'm doing. Okay, so we've got 7, 98, 25, 19, and 26. Okay, hopefully you notice every time I enter a number I hit an enter to put the data point in there. Okay, alright, so you can see what I'm doing a little better. I'll go ahead and go back out to the big screen. So now what? Well, I'd like to get the mean of those data points. Well, we're going to use OneVar stat to do that again. So I'm going to hit a second and a quit to get back out to the home screen. Hit clear here just to give myself a clean workspace. And then we'll go Stat, Calc, OneVar stat, and now my data this time reside in L1. And remember that L1 through L6 reside as second functions for the keys 1, 2, 3, 4, 5, and 6 on the calculator. So go second, and the number 1, we get an L1, hit an enter, and we get back X bar is equal to 35. Okay? Now does that seem like a reasonable measurement of center for Kim's test scores? Well, if you think about it, it doesn't, right? We see that all but one of her test scores is lower than that, and that's supposed to be a measurement of the center of the distribution. Okay, so what you may or may not have noticed here is the way this data is spread out. So let's just do a real sort of quick hacked out frequency plot here to kind of get an idea of what this data looks like. Is that we notice that we get most of the data. There's, say, the 7, and then we've got like the 19, and then here's the 26 and the 25 right next to each other. In other words, all of these data, if we were to put them as a frequency plot, wouldn't look too dissimilar to something like that. And then all of a sudden, here's this 98, which is way over here all by its little lonesome. Okay, so the thing to notice is that 98 is a long ways away from the rest of the data point. And as it turns out, the mean has a physical interpretation. The physical interpretation of the mean is it's actually the balance point. If you were actually to take your data and do like I've got and put them on a balance beam here, the mean turns out to be the spot where you have to put the fulcrum in so that the whole thing balances. Okay, it physically would really turn out to be that. If you built this out of a piece of wood, that's where you'd have to put it. Okay, so the thing to notice is that what happens is that this mean right here of 35, okay, got pulled towards the extreme value, didn't it? Okay, it got yanked way up here towards this 98 to try and keep things in balance. And so that's one of the flaws to the arithmetic mean is that it's sensitive to extreme values. One way to remember that is to say that the mean loves extremes. It gets dragged towards them. Okay, well, hopefully you got all that. That's really what the point of this LDI was all about, was to get you start thinking about the mean getting dragged towards those large or small values in a distribution. And we'll see you back here for LDI 5.2.